Hajime Mashite, Watashi wa Karan desu.
Watashi wa Mahir desu.
Watashi wa Mohammed Hani desu.
And today we'll be talking about our project, Factory Intelligence. So before we start with our project, let us talk about our creditability. I, Karan Karkira, am a robotics and AI engineer that has worked on autonomous lane painting robots, a autonomous no GPS drone, as well as a robotic arm. Now moving on to my teammate, Hani.
Pursuing robotics and AI, I'm very well versed in this domain. I've worked with LLM, deep learning, neural networks, etc. And coming to the robotics part of side, I've worked with autonomous mobile wheel robot, manipulators using ROS, etc. Which gives me a very good foundation in the area. Now I would like to give it to Mahir.
In this problem statement, a lot of AI is involved, and I'm very well versed with the AI environment. So I've worked on AI assistants, offline AI assistants, on multiple AI models, and also AI agents, and image to voice AI. All this will be implemented or used somewhere in our project. Now, coming to our project, our main objective is implementing and improving flow of objects using wheel-carrying mobile robots. And after that, we aim to reduce loss of efficiency and provide safety. So in a factory environment, the big issue is safety for the humans. So by minimizing the use of manual labor, we implement UGVs or Unmanned Ground Vehicles and ensure safety. And all this will be done by collision avoidance in static and dynamic obstacles. Now coming to our core concepts, how we want to implement this project. So first of all, there's path planning and collision avoidance. So when we do path planning and collision avoidance, there are UGVs. So when there are multiple UGVs in a very cramped environment, path planning and collision avoidance will help. And then there is queue management and system metrics. So when there is a factory, there will be a lot of materials processing, materials incoming, materials outgoing. So all that will be used by queue management, such as priority queuing. Let's say there's something important, so that will go first. And motion control and performance optimization. So we have to reduce the computational load because it will be expensive. So for that, we have optimized motion control and performance optimization. Then, and for the business model, efficient and cost effective. So current UGVs are very costly and very less efficient. Our model aims to reduce that by improving efficiency and reducing the cost. This is a flowchart for a proposed solution. It's going to showcase how the whole system works. Moving on, we go to a software prototype simulation. As you can see in this simulation, we have incoming materials in this in container. The cranes will put it onto the UGVs, which will carry it to those processing stations. After the materials are processed, that is in C1, C2, C3, C4, all that are processing stations. After they are processed, they will be transferred using UGV to the outgoing storage, where it will be stored until an order comes. Once an order is asked, it will be taken by the UGV again to the delivery pickup area, where trucks will be waiting, and once the buffer is reached, trucks will take it to the delivery stations. All this is done with path planning and collision avoidance and with minimal human effort. As you can see, all of this is Japanese industry compliant, and as you can see, with this configuration, we are achieving much more efficiency than normal human setup. That is up to 80 to 85%. And as you can see, if you go up, there is a throughput of 674 materials. That's way too good. And this is all done by this simulation. And if you go down, and if you see the matrix right here, the average time for this whole thing is 36 seconds. And system efficiency, system load efficiency is 100% utilization. Nothing is wasted, no energy is wasted, no resources are wasted. We also can see the storage status. We also can see the number of orders delivered, that's 54 hours. And their battery that is used by the UGVs are 30 to 40%. And the performance, as you can see, is performing very well. Now I would like to call my teammate Mohammed Hani, tell us more about the project.
Talking about the differences between ours and the existing. First of all, ours has the predictive avoidance systems, which results in zero accidents. Now, it also has real-time monitoring systems, and it also comes in built-in Japanese regulatory compliances. And talking about the costs, ours is way more cheaper as compared to the existing ones. Now, talking about the practicality and scalability, ours aligns with the real automated logistic workflows with energy-aware features. Now, it can handle fleet sizes from 1 to 50 as shown here, and it also reduces the computational load drastically.
Now, talking about the impact on the industry. It provides a productivity boost while having an energy efficient system that can transform a workflow that enables human and robots to work together in an harmony. Now moving on to the Indo-Japan relevance, the IJDP, that is Indian-Japan Digital Partnership, provides a collaboration on AI, IoT as well as robotics while enhancing competitiveness through innovation and allowing a collaboration between India and Japan for technology and skill sets. With this, I would like to conclude our presentation and call upon my teammates Mahir and Hani.
Coming to our references for this project. So, the current industrial applications are very expensive and are very less efficient. Our project aims to overcome those problems and be something more advanced.
Coming to an end, we are extremely grateful for this opportunity and we would love to work with your help and guidance.
Arigatou gozaimasu.